In this video, we're going to look at jitter and phase noise in oscillators. We'll look at their basic definitions and metrics, and we'll also cover their typical characteristics in integrated circuit oscillators. We use oscillators to produce periodic waveforms, like this one. In some applications, we care about the precise shape of the waveform, but most of the time, we just care about its periodicity. So a periodic waveform should repeat at regular intervals. An ideal clock would maintain the same period, labeled here T sub 0, over and over and over again. But a real clock will deviate from this ideal. So we define absolute jitter as the timing deviation of real clock edges from their ideal positions, which should be uniformly spaced with spacing of some period T sub 0. So we can define here the sequence T with integer subscript k as the timing when this waveform hits a particular phase. It's natural to use, for example, the rising edge of a clock waveform. So this waveform here is thought to be a fully differential waveform, so it crosses through 0 at regular intervals. We define each rising edge 0 crossing as T0, T1, T2, and so on. And although they should be perfectly spaced with the same spacing T0, they deviate away from those ideal crossing instants by the sequence tau sub k. So with these definitions, T sub 0 is the mean clock period, and the sequence tau is called the absolute jitter sequence. And tau, as defined here, has units of seconds, but we can also define a related sequence, phi sub k, being the same sequence but in radians. So we normalize by the constant 2 pi over T0. So both tau k and phi k are measures of absolute jitter. Unfortunately, although simple to understand and define, it's very difficult to observe or measure absolute jitter because it relies on comparing a practical clock waveform to some ideal jitter-free clock waveform, which doesn't exist in practice. Nevertheless, absolute jitter is a very useful concept that we'll use to make basic definitions and to aid in our understanding of the behavior of jitter. Here's a simple example to illustrate how random noise sources in electronic circuits, such as thermal noise, can translate into absolute jitter. Let's imagine that the current source I here is generating a sinusoidal waveform or other periodic waveform that is ideal. But the resistor R is going to produce some thermal noise. This can be modeled, as you know, by either noise current source in parallel with I or a voltage noise source in series with R. In either case, it causes the voltage waveform at V to deviate from its perfectly periodic shape, as shown here. Let's say that the voltage noise that appears at V has a variance, sigma n squared. It's going to disturb the sinusoid's zero crossings by an amount equal to the voltage noise that appears at any of the zero crossings divided by the sinusoid's slope at the zero crossings. Let's say the sinusoid has an amplitude A and a frequency omega naught. The slope of the zero crossings is A times omega naught. Therefore, each zero crossing will deviate from its ideal value by an amount tau equal to the noise sample, let's call it VNK, sample of voltage noise that arises at that zero crossing, divided by the slope A omega naught. Now, if we're interested in the variance of that absolute jitter sequence, tau, okay, it's going to be related to the variance of the noise voltage samples, sigma n squared, by that slope. Finally, we can re-represent the absolute jitter variance in terms of radians by simply normalizing with respect to the constant 2 pi over t0. Remember that omega naught is related to t0 as follows, t0 being the period of the ideal sinusoid. So that results in some cancellation, and the jitter sequence in radians has a variance that's related to the voltage noise variance, very simply, as shown here. Here's a numerical example to drive the point home. Let's say that the amplitude of the sinusoidal current here is sufficient to produce a voltage sinusoid at the output with an amplitude of 1 volt. Let's also say that the value of the capacitance is known to be 1 picofarad. As a result, regardless of the value of R, we know that the variance of the voltage noise at V is going to be given by kT over C, which at room temperature is about 64 microvolts squared. We can use the formula from the last slide now to find the resulting timing absolute jitter, sigma tau squared, by plugging in the variance of the noise voltage. Here's the amplitude of the sinusoid. And finally, the frequency is given 1 megahertz. The result is an absolute timing jitter of 12.2 picoseconds. When we're expressing it as variance, of course, it's actually 10.2 picoseconds squared. We may also say that the output waveform has a jitter of 10.2 picoseconds RMS. Since the square root of the variance is the root mean square timing jitter. So far we've defined two discrete time random processes that capture the jitter of a periodic waveform. We defined absolute timing jitter in units of seconds as the discrete time sequence tau k. And then we also defined the phase absolute jitter being basically the same sequence expressed in radians, and we called it phi k. So these are time domain representations of the absolute jitter. As with any random process, we can obtain a frequency domain representation by taking the Fourier transform of the autocorrelation of either of these discrete time random processes. So if we do that for the phase jitter sequence, we define the resulting power spectral density with an S subscript phi, and that then is the so-called phase noise. Essentially, a frequency domain representation of the absolute jitter in phase. Mathematically, it's written here. And remember that it's got units of radians squared, since it's a measure of the power spectral density of the discrete time sequence per unit frequency per hertz. Now we can obtain the total variance of the phase jitter by integrating this power spectral density, the phase noise, over all frequencies. Remembering that the underlying process is just defined at the zero crossings of the periodic waveform. It's a discrete time random process, and therefore the upper limit of integration is not infinity, but is 1 over the sampling rate of the discrete time process. You'll sometimes see this written simply as infinity because it's fairly high frequency. It's obviously related to the frequency of the clock that we're measuring. But strictly speaking, it does have an upper limit of integration here. So integrating over all these frequencies gives us the variance of the phase sequence phi, and then we simply can normalize it by the period of oscillation and 2 pi radians to get the variance of the absolute jitter. Now this will have units of seconds squared. We can take the square root of that and obtain the absolute jitter root mean square value. It's just one number that really captures the variability of the clock waveform from an ideal periodic clock. And it is related to the phase noise by this integral. As we mentioned, it's not very practical to measure the absolute jitter because it requires a perfect clock reference to compare with. But it is possible to compare periods of the clock with previous periods of the clock. So this leads to a related but slightly different series of performance metrics that we're going to talk about next. The simplest of which is the period jitter. So let's think again about our clock waveform. And at first we defined the absolute jitter sequence as the deviation of the zero crossings from their ideal times. But instead, let's define a discrete time process for the periods of the clock waveform. So let's say here's the first period, here's the second period, oops, should have taken that just to the rising edge to stay consistent here. Here's the next one, T3, and so on. So defining the sequence, capital TK, we can see that it's related actually to the absolute jitter sequence. So if if let's call this arbitrary period here, tau k, we know tk, sorry, we know that this time is tk, this one here is tk plus 1. So clearly, capital TK is just the difference between tk plus 1 and tk. Now we can write each of these in terms of the nominal period and the sequence of absolute jitter, tau k. So specifically, k plus 1 t0 plus tau k plus 1 minus k t0 minus tau k. So if we go one step further, we'll see that all we're left with is this relationship here. Tk is the nominal period plus the deviation of this rising edge from its ideal point minus the deviation of this edge from its ideal point. Now this makes sense because if both of those rising edges were a little bit late in an absolute sense, we wouldn't observe that by looking just at the period tk. Tk would still be its nominal value of t0. If both edges were early, then again, we wouldn't be able to observe that in tk. It's when one is early and one is late that we start seeing a difference in the period tk. Now, clearly, for any decent clock, the jitter, the sequence of periods tk would be centered around t0, its nominal value. So we're probably, in measuring jitter, only interested in the deviation of the clock periods from their ideal value. So we're going to define jk as just this sequence here. This is the so-called period jitter sequence. It's a sequence of numbers that tells us how far away in seconds each clock period is away from its nominal value. And this is something that is easily measured on an oscilloscope, for example. You can imagine triggering an oscilloscope on one rising edge and then looking at the next rising edge. You would see that most of the time, this subsequent second rising edge would be at very close to t0 seconds after the trigger, but it wouldn't be perfect. It would vary somewhat, and we could measure that variation over many, many measurements with a high persistence on the oscilloscope and take its RMS value, and then that would give us a statistical measure of the period jitter, RMS. Now, the interesting thing that you'll notice is that this period jitter sequence JK is related to the absolute jitter sequence by simply a discrete time differentiation. So if we imagine the signal flow here, if we have an absolute jitter sequence tau k, and we put it through a 1 minus Z inverse filter, what we get out is the jitter sequence, jk. So when we're looking at the jitter sequence jk, which again is something that we can look at on an oscilloscope, for example, what we're seeing is a filtered version of absolute jitter, filtered by this discrete time differentiation. Its frequency response is a sinc function, so that's captured by this term here. So when we, if we observe the spectrum of the jitter sequence jk, we will see the phase noise filtered by this 1 minus Z inverse response. What does a differentiation filter look like? Well, it's got a frequency response that at low frequencies is 0 and then increases. So this makes sense. If we think of absolute jitter that has low frequency content, that physically would mean that rising edges of the clock are slowly moving back and forth in time, so that the difference between one rising edge and the next one wouldn't be very much, right? The variations at, due to low frequency phase noise are arising and disappearing very, very slowly. And so such jitter would be not evident just by looking at any individual period of the clock waveform. On the other hand, high frequency jitter means that subsequent edges are moving back and forth very rapidly compared to each other. So that type of absolute jitter, high frequency absolute jitter, does show up by looking at the period of the clock waveform. So that's our intuitive understanding for this sort of filtering. When we look at period jitter, we're really mostly just looking at the high frequency part of the absolute jitter. Now we can find the variance of the period jitter by taking this filtered phase noise and integrating it over all frequencies. And then finally, we just have a normalization to get back to units of seconds. So that's just a quick intuitive explanation for the relationship between period jitter and phase noise. Rigorous derivation of this equation is a little bit more involved, of course, but hopefully that gets across the key points. Now this idea can be extended further. Rather than look at and comparing the duration of any individual period to its ideal value, we can look at any two periods and compare it to their ideal value. And we would expect any two periods ideally to have a duration of 2t0, but we know that because of jitter, it's going to deviate from that value. So we call this sequence of deviations the two-cycle jitter. And we'll use this notation, J2 subscript K. And then we can take this measurement over and over again, of course. Oops. And here's always called J2 because we're only looking at the two-cycle jitter, and now we're at K plus 2, and so on. So we get another discrete time random process. Now, this sequence, J2K, is obtained similar to the way in which we obtained the period jitter as a filtered version of the absolute jitter. This two-cycle jitter is the absolute jitter filtered by, instead of 1 minus Z inverse, it's 1 minus Z to the minus 2, because we're looking at, each observation looks at or is sensitive to the timing deviation of one rising edge and a rising edge 2 clock cycles later. Doesn't really matter what's going on here. It doesn't have any impact on this measurement here. So the sort of measurement at every time step k depends on k and k from 2 time steps ago, in a sense. And we can generalize this idea to the so-called P-cycle jitter. This is what we showed here is really can be thought of as a special case for P equals 2. The period jitter that we defined in the last slide was really also a special case of the P-cycle jitter where P equals 1. But in the general case, we've got this jitter sequence using this notation here that's obtained by taking the absolute jitter sequence and passing it through a filter that looks like this. Now, any P-cycle jitter is like the period jitter, not too difficult to observe in a lab. Again, you just trigger off a rising edge of this clock, and you look at the rising edge that comes 2 periods later. For the 2-cycle jitter, 3 periods later, for the 3-cycle jitter, and so on. And if you take each of these measurements, what you're actually looking at is differently filtered versions of the absolute jitter. And the jitter filters are represented by this term here. They're captured by this sine squared term. And depending on the value of P, you're going to have different magnitude responses for this jitter filter. And therefore, the P-cycle jitter you observe will be sensitive to different parts of the absolute jitter spectrum, or phase noise, as we call it, depending on the value of P. So we already saw with P equals 1, the regular period jitter had a shape like this. P equals 2 is going to look something like this. Actually, I didn't quite draw this right. I should have looked more like this. And then you can get P equals 3. I may not be drawing these perfectly and so on. So here's, I'll try and draw this P equals 1. P equals 2. P equals 3, and so on. I just wanted to sketch a few so you see the trend. The trend is that as P increases, we start capturing more and more low frequency content of the absolute jitter or of the phase noise in the P-cycle jitter measurement. This makes sense because as you increase P, you're looking at rising edges that are further and further apart. So for example, consider an extreme case where P equals 1,000. Well, even quite low frequency jitter, quite low frequency parts of the phase noise will show up if you wait 1,000 cycles. So it's not surprising that when we take the integral of phase noise to find the P-cycle jitter with P equals 1,000, it wouldn't be surprising that we're capturing some of that low frequency phase noise inside this jitter filter here. So this fact has been observed by some and recognized as a way to essentially measure the absolute jitter and its phase noise even at low frequency by combining a number of P-cycle jitter measurements for different values of P. Each different measurement for a different value of P gives you information about a different part of the phase noise spectrum. So we've defined the phase noise as the frequency domain representation of this absolute jitter sequence, which we've said is not easy to observe, but other spectral representations of jitter can be much easier to observe. So for example, if we think about this jittery sinusoid, the voltage waveform that arises here, Vt, can be straightforwardly turned into power spectrum, and we would see a spectral density like this one, S subscript V, that is centered around the nominal oscillating frequency, 1 over T0. If there were absolutely no noise, no jitter, then Vt would be a perfect sinusoid, and so this frequency spectrum would be a pure delta function right at 1 over T0. But we're going to have some noise, we're going to have some jitter, so instead what we see is that delta function spreads out a little bit. Okay, its peak doesn't become infinite, obviously, so it's got a finite peak here in this power spectrum, and we see skirts on it going to higher and lower frequencies. Now, the more noise, the more jitter we see on VT, what we will observe qualitatively is that we will get more spreading in the spectral representation. So a pure clock is going to be closer to this delta function. It's going to be very narrow in the frequency domain. So this appears to be kind of a nice, intuitively a nice way to measure the quality of a clock and its jitter. And it turns out that this power spectrum, SV, is quite closely related to the phase noise, S subscript phi. Before we get there, let's recognize that SV should have units of volts squared per hertz, since it's the spectral representation of a voltage waveform Vt here. And to sort of remove some of the ambiguity, we often will normalize SV and plot instead a normalized version of it, where this subscript, script of L is usually used as the symbol. So this script L is the spectrum of SV with the spectrum sort of recentered around 0. So we take that whole spectrum SV and shift it down to DC. So that's what we're doing here. We're, instead of plotting SV, we're sort of plotting SV, but as a function only of delta F, how far away from the mean frequency 1 over T0 we are. Right? So we plot L now as a function of delta F. And the second thing we do is, if we're interested in jitter, mostly we really care about, again, the deviations in the clock phase away from its ideal value. We care less about the amplitude of the sinusoid. So we just normalize the spectrum SV to the total power in the sinusoid. Also called the carrier, in reference to the use of sinusoids to carry information, to be modulated and carry information for RF applications. So the resulting spectrum here, this script L, now has been normalized by something with units of volts squared. So it has simply units of 1 over hertz. But we will most often plot it on a logarithmic scale. So we express it in decibels, take that power spectrum, take 10 log base 10 of it. And so now we've got something with units of decibels normalized with respect to the carrier power. So rather than dBm or dBV, which are logarithmic units normalized to milliwatts and volts respectively, here instead we define dBc, decibels with respect to the carrier power. But it's still a power spectrum. It's per units of frequency per hertz. So you get these funny units here, dBc per hertz, for this script L, which is essentially just a normalized version of the power spectrum of the waveform V itself. So this is obviously not too difficult to measure, for example, in a lab, just using a spectrum analyzer. This can be measured. Now it turns out, although we're not going to derive this, it turns out that as long as the phase noise is not excessive, and by this I mean even for quite practical levels of phase noise, this script L is very simply related to the phase noise that we defined in terms of absolute jitter, just by this factor of 2 here. So this equivalence is, again, quite accurate so long as the phase noise is very, very small. So unfortunately, because of this relationship, it can lead to some confusion. We very often use units of dBc per hertz in reference to phase noise, whereas we've already said that phase noise really has units of radians squared per hertz. Using these units here can be more confusing because it's not evident how integrating something with units of dBc per hertz and then gives us something with units of radians squared. But one way you can sort of make sense of this is to recognize that dBc is a sort of normalized quantity that is actually dimensionless, and so are radians, in fact. Radians are, strictly speaking, dimensionless because it just expresses something as a fraction of total circumference of a circle, essentially. So mathematically, this problem of the units should pose no problem. It's just nice to keep in mind these different definitions. You'll also, I should say, see the symbol script L often used directly in reference to phase noise rather than this notation here. So essentially, these two quantities, the script L and the S, are often used interchangeably. There's a factor of a half to take care of in there. So all this can make the use of these terms a little complicated and confusing. But the underlying reason is that as long as the phase noise is small, the two become equivalent. One important difference that arises, though, and which I'll point out now, is that clearly this script L is always going to have a finite density, power spectral density, even all the way down to 0. Because if it shot up high, then it's possible that the integral under this curve would diverge, and that would predict infinite power at the node V, which obviously isn't the case. However, the same is not true for phase noise spectra. Phase noise spectra often do shoot up to very, very large values at DC, and in fact their integrals, if taken all the way down to DC, often diverge. We can talk more about that later. It doesn't pose a practical problem, but it is an important difference between the way we've defined script L here and the way we've defined phase noise. Another metric we use to quantify the quality of a clock is the probability density function of the jitter. So you can imagine taking a bunch of measurements of the jitter sequence tau k, or for that matter of any p-cycle jitter, and plotting a histogram of the observations you make of that discrete time random process. Now in the case of tau, we would expect the mean to be 0, but you're going to get a spread of values around 0. The wider that spread of values, the more absolute jitter we're seeing, the more variance we would expect on tau. Essentially, the more jitter we have and the less pure of a clock we have. So this histogram, this probability density function, provides a lot of information about the quality of a clock, but it's not the same information as the power spectral density with phase noise. For example, shown here on the left is a Gaussian distribution function for the probability density of absolute jitter. Now you can have a Gaussian distribution and have phase noise that's white or phase noise that's colored. That doesn't mean that, in both cases, you can still have a Gaussian PDF of the jitter. So it doesn't really tell you much about the spectrum of the jitter or the frequency content when you look at the PDF, but it can tell you other interesting information. And again, it's relatively easy to measure this. For example, if instead of this Gaussian distribution here, you have a distribution with a different shape, such as the one shown here, that might suggest to you that the underlying cause of the jitter is not random thermal noise that's arising in the circuit itself, because thermal noise arises because of the superposition of many, many independent noise events. So it pretty much always shows up with a Gaussian distribution. If you see a non-Gaussian distribution, that's a clue that something else is causing the jitter. For example, there may be power supply noise, or there may be some other deterministic interference that is muddling the clock. The distribution I chose here is kind of reminiscent of a sort of sinusoidal waveform that spends most of its time at the extremes and less time in the middle. In any case, the main point here is that the probability density function of the jitter is another useful metric that we can measure and observe that helps us understand the jitter that is complementary to the phase noise, provides different information. A really important example of when we might be even more interested in this PDF of jitter than we are in its phase noise is if we imagine using the clock waveform to clock some digital logic circuits. In such cases, we have to allow enough time for the logic values to propagate through some logic gates before a neighboring clock edge arrives. So we're often interested in what's the earliest, the absolute earliest when we can expect the next clock edge to arrive. Now, if the PDF is Gaussian, then we know that there's a very long tail on Gaussian distributions. So it becomes a matter of probabilities. How often are we willing to tolerate an error in the logic operation? Likely we would want that to occur very, very infrequently, once in the history of the universe or something like that. So we would want to ensure that the tail of this distribution or the variance of this distribution is tight enough that we respect some minimum clock period, sort of over, for a huge fraction of the time. On the other hand, if the PDF is non-Gaussian, it may be quite limited. It may be much easier to ensure that the period respects some minimum value. And again, this information wouldn't be evident by looking at the phase noise on its own. We can integrate the phase noise and obtain an RMS value for jitter, but that doesn't tell us the shape of the distribution. That doesn't tell us whether it has a long tail or whether it's cut off as shown here on the right. Both these two shapes could have the same RMS value, but they might have very different implications when it comes to a worst case clock period. Next, we want to understand the jitter and phase noise characteristics that typically arise in integrated circuit oscillators. And to do so, we're going to make use of a linearized model for the analysis. So just a quick caveat here, linearized analysis is generally not going to be accurate for oscillator circuits because oscillator circuits generate quite large waveforms. And so as a result, transistors operate non-linearly and small signal analysis is generally not applicable. But still, linearized analysis is quite useful because the conclusions derived still predict real-world behavior, and it's much easier to intuit the behavior and to perform closed-form analysis than using nonlinear models. So, having said that, here's a simplified linearized analysis of an oscillator, modeling it as a negative feedback loop with a open loop gain L. And it's the case that if the frequency at which L has a 180 degrees phase shift, which we'll define as omega 180, gives rise to an open loop gain L greater than 1, then the circuit will oscillate. You can think of the operation as if there were some input to the oscillator circuit, which is nominally 0, but where any tiny noise event, even a single electron worth of noise, can initiate some oscillations in the circuit. Now, the closed loop response of this feedback loop here we'll call G. G can be the closed loop linear response when oscillations are just starting. So there are relatively small signals only present in the loop. And G equaling 1 L over 1 plus L will have right half plane poles in this case. The right half plane poles predict that for even a tiny impulsive input, you'll get sinusoidal oscillations with exponentially growing amplitude. Now, before very long, the growing amplitude of these oscillations will cause some transistors in the circuit to change, perhaps from active mode to enter triode. As a result, their small signal transconductance will decrease, and so the loop gain L will change if you want to continue using this linearized approximation, which, as I said, is somewhat fraught. But in any case, it's not too hard to imagine that the resulting loop gain L decreases once the amplitude gets very large and some components start saturating. And as a result, the closed loop response G has poles that shift back to the j omega axis. So again, in this scenario, especially here, the linearized analysis is not expected to be perfectly valid, but it does result in the observed behavior. The model predictions do confirm the observed behavior, which is that the oscillation amplitudes saturate and then become constant. So you can imagine that is happening when the closed loop poles G end up lying exactly on the j omega axis. So in this condition, where the poles of G lie right on the j omega axis, it has a frequency response as shown here. These poles cause the magnitude response of G to shoot up to infinity right at the frequency f0, which is the frequency of these poles on the j omega axis and is the frequency of steady state oscillations. Now, with a frequency response like this, we expect that any white noise that may be introduced into the loop, for example, due to thermal noise of any transistors or resistors connected in it, get shaped by this frequency response G. Rather than plotting G, we can also normalize that frequency response and plot it as a function of delta F, where delta F, as in the definition of phase noise, is sort of a frequency deviation away from the nominal oscillator frequency, F0. So plotting this response normalized with respect to delta F and plotting it on a log scale, a dB scale on the y-axis, you'd see that as you increase delta F and you move away from the oscillating frequency F0, this magnitude response rolls off with a slope of 20 dB per decade in response to these poles in the j omega axis. So white noise introduced here will get shaped by this 20 dB per decade response. So as a result, the phase noise that arises at the output we can expect will have a similar shape. Certainly the script L, which we've already said is a good approximation for the phase noise. Again, in response to white noise introduced anywhere into the oscillator loop is going to have a shape like this, rolling off at 20 dB per decade. And indeed, as a result, we do observe in integrated circuit oscillators phase noise with a shape that rolls off at 20 dB per decade over a wide range of frequencies. Now, that's not the only source of phase noise in integrated circuit oscillators. Other subtle types of noise can give rise to other spectral densities in the phase noise at the output of an oscillator. So, for example, if we consider a simple differential pair circuit that's subject to periodic waveforms with large amplitude at their input, you may know that the resulting drain current at the output of the differential pair is given by this tail current upconverted or multiplied by the voltage waveform at the differential pair input. So when you have a tail current source here in this differential pair that introduces some noise, that noise ends up upconverted by the oscillator clock waveform to appear around the oscillator output frequency. So typically the transistors making up this tail current source will have noise that includes both white noise thermal noise and flicker noise with a power spectral density of 1 over F. Now both of these noise terms are upconverted to the vicinity of the output frequency F0. So and you might end up with some noise like this around F0 here. Again, this is sort of qualitative picture to aid in understanding these particular power spectral or noise spectral densities may or may not be easy to observe. But then following our linear model here, we know that this gets then filtered by G, which further shapes the noise spectral density by our minus 20 dB per decade filtered. And so as a result, the white noise from the tail current source shows up as our familiar 20 dB per decade phase noise at the output, proportional to 1 over F squared. But it's the flicker noise that gives rise to a new component in the phase noise. This flicker noise shows up in the phase noise at the output of the oscillator with a term that's proportional to 1 over F cubed. And as a result, rolls off with this strange slope of minus 30 dB per decade. And that's coming from the minus 10 dB per decade of the flicker noise, shaped by the 20 dB per decade indicated by the linear model for the oscillator. And so that gives rise to a more complicated phase noise spectrum at the output that has these two regions. At low enough frequency, the flicker noise will dominate, and the phase noise can be expected to exhibit a slope of minus 30 dB per decade. At high enough offset frequencies, however, you end up with upconverted white noise dominating and resulting in a phase noise spectrum that rolls off at minus 20 dB per decade. And as indicated here, the 1 over f cubed region is typically arising from something like a tail current, whose flicker noise then is somehow upconverted by the large periodic waveforms running around the oscillator. So in summary, we expect and we indeed see for integrated circuit oscillators that the phase noise has a response that includes a 1 over f cubed term rolling off at 30 dB per decade, and a 1 over f squared term that rolls off at 20 dB per decade. We can model that here, the term proportional to f squared, and with different constants of proportionality labeled here h3 and h2. And then finally, as we saw in our simple toy example, anytime we've got white noise superimposed on a periodic waveform, that's going to give rise to a white noise spectral density at the output, white phase noise at the output. So for example, if the output of that oscillator is buffered by even a simple resistively loaded diff pair or a CMOS inverter or anything, then we'll certainly see some white noise superimposed on the clock waveform, and that gives rise to a third part of this curve that's just white noise. That's flat, and so that's captured by this constant term H0. So we can basically write out an expression, general expression, that captures the phase noise of integrated circuit oscillators with these three dominant terms. And finally, we got the H3 term here. Now, although a real phase noise plot will show these three terms blurred together and may indeed have other effects showing up, still it's almost always possible to clearly discern three different frequency ranges where each of these three phase noise components are dominant. Precisely where these break frequencies arise, of course, depends on the values of the constants H0, H2, and H3, which in turn depend on the design of the oscillator. But it's certainly always the case that at high enough frequency, the white noise will dominate. At low enough frequency, the minus 30 dB per decade 1 over f cubed term will dominate. And in any really practical integrated circuit oscillator, those two corner frequencies are separated by enough that you can almost always clearly discern a region in between there where minus 20 dB per decade is dominant. Finally, I should point out that this is the phase noise characteristic that we observe for an oscillator free running on its own and generating a periodic waveform at the output. If you take that clock waveform at the output of the oscillator and feed that back as part of a phase lock loop to adjust the voltage control on the oscillator, then you've kind of placed this whole circuit inside of a larger feedback loop that filters this phase noise, and we'll talk more about that in a future video. But in such cases, the phase noise that you observe at the output of the phase lock loop will be a filtered version of this, will not look quite like this. So here's the plot of typical oscillator phase noise. Of some interest may be this corner frequency Fc that marks the transition between the 1 over f cubed region and the 1 over f squared region. It's not difficult to solve for that point. In the vicinity of Fc, it's safe to assume that the phase noise is well modeled by just those two terms. We can safely neglect the white noise term. Again, around here certainly, and we can solve for the corner frequency being the point where each of these two terms contributes equally. So that h2 over fc squared is exactly equal to h3 over fc cubed. Now rearranging, you can simply solve for fc in terms of the two constants. It's h3 over h2. And that's the expression shown here. This brings us to what some people find to be a confusing aspect of phase noise. Now we've said that phase noise or jitter is the integral of phase noise, and we've also said that in practice phase noise looks like this. It has this component at low frequencies that is proportional to 1 over f cubed. Now if we integrate the area under such a plot all the way back to DC, we find that the integral diverges. And so what do we make of this? This suggests that the absolute jitter of a practical oscillator output is in fact infinite. Now, although that seems problematic at first, if we think a little bit more carefully about it, it's indeed the case. The first thing to point out is that the integral diverges quite slowly, so you have to go to very, very low frequencies. You have to integrate this phase noise down to very, very low frequencies in order to see the jitter increase dramatically. And what does looking at very, very low frequency phase noise really mean? Well, it means that looking at the clock over a very, very long window of time and considering how stable those edges are, how close are they to their ideal value. Now, if you do that in the lab, what you actually find is that, if you start with one edge, any one edge, and you look at the next one, you will find that, well, it deviates away from its ideal value by a little bit. And we've quantified that in terms of the period jitter. If we look at the second edge, it deviates a little bit more. That's what we call the 2-cycle jitter, and then the 3-cycle jitter, and so on. And as you observe over a longer and longer time horizon, you find that the clock edges deviate by more and more and more as you go along. And that's because you're looking at lower and lower frequency components of the phase noise, and we've seen that the very low frequency of the phase noise increases without bound. Now in the limit, if you waited for days, weeks, months, or years, the edges would become really unruly and would be very far away, most likely from where you expected them to be. At some point, you've waited so long that this becomes indistinguishable from simple drift or aging of the circuit. I mean, there's an analogy here between very low frequency phase noise and low frequency flicker noise, which also appears to suggest very large amounts of noise at very low frequency. And perhaps it's not surprising that the 1 over f cubed term in our phase noise plots actually arises from flicker noise in most cases. But in any case, these jittery edges do accumulate. The jitter in subsequent clock edges accumulates over time, and as a result, the absolute jitter increases without bound, which is yet another reason that absolute jitter is a little bit difficult to wrap our brains around. Now, this classic paper referenced here describes the evolution of p-cycle jitter over time. And what you see is that if you measure the RMS value of the p-cycle jitter for different values of p and plot the two on a log-log scale, you interestingly observe two different regions. For a while, the p-cycle jitter increases slowly. That is, it increases in proportion to the square root of p. And it does this so long as the filtered phase noises that are giving rise to the p-cycle jitter are concentrated, the jitter filter applied in that integral is concentrated in the portion of the phase noise spectrum that rolls off with 1 over f squared. So as a result, if you could see this actually analytically just by neglecting other terms in the phase noise and assuming that the integral is really concentrating only on that part of the phase noise plot. And you can get an analytical result like the one shown here that suggests that the p-cycle jitter simply increases in proportion to square root p. Now for p large enough, we already saw that the jitter filter will eventually end up including terms at very low frequency where 1 over f cubed phase noise dominates. So at that point, the p-cycle jitter starts increasing more quickly. As we further increase p, now we're capturing very large increases in phase noise. And this plot on a log-log scale will therefore go from having a slope of 0.5, where the plot's proportional to square root p, to a slope of 1, where the p-cycle jitter becomes proportional to p. Now you can take a series of these measurements for different values of p and plot them and fit lines to them. And that's what's done in the paper. And you can observe this crossing point. There's a particular value of p where the plot appears to transition from this best fit line to the best fit line with a slope of 1 at large values of p. Now that transition value of p is related to the corner frequency fc, where we go from being dominated by 1 over f squared noise to being dominated by 1 over f cubed noise. So this is really interesting because this p-cycle jitter measurement is something that's pretty straightforward to take even with a scope, and yet from a series of these p-cycle jitter measurements, you can infer the corner frequency fc of the phase noise plot. Now obviously this is all predicated on assumptions about the phase noise, namely that it's well modeled by these two terms, the 1 over f squared term and the 1 over f cubed term. But again, that is quite an accurate model in practice, and so you can indeed generate these plots and use this inference in a lab. Finally, let's quickly do a numerical example. Let's imagine that the measurement described is performed on a 1.5 gigahertz oscillator, and that it was found that this corner point arises at PC equals 30, so 30 cycle jitter is where we transition from 1 over f squared phase noise to 1 over f cubed. And let's also say that one particular data point here at PC equals 10 corresponds to a 10 cycle jitter of 2 picoseconds RMS observed. So those two pieces of information together can be used to come up with a model for the phase noise of the oscillator. First, we know that in the 1 over f squared region, we have the relationship shown here. The period of oscillation T0 is simply 1 over 1.5 gigahertz. And we can use this combination here. This isn't PC, of course. We can use P equals 10 and 2 picoseconds, plug it into this expression, and solve for H2. And then we can use the corner point here, plug that in to find the corner frequency FC of the phase noise, and doing so reveals a phase noise corner of 2 megahertz. And then finally, that 2 megahertz is used to relate H2 and H3, and so from that we find H3. So having found H3 and H2 up here, we've got a model for phase noise as shown here. Here's the 1 over f squared term with constant H2, and then we've got the 1 over f cubed term over here with constant H3. And you see that we've neglected the white noise term here. In general, there may be another term H0 that's constant, but that would really only predominate at very high frequencies. So we end up with a quite useful model for phase noise covering these two regions here. The 1 over f squared region and the 1 over f cubed region over here. And with the corner frequency FC in between.